So good afternoon, everyone. So welcome to, sorry, good morning, everyone. So welcome to the lecture 29 of the course on data structure and algorithm. So today is our first class where we shall start discussion on the nonlinear data structure part of the course. Okay. So today we shall introduce with the basic fundamental concepts of a tree nonlinear data structure. Okay. So let me share my screen. So can you see my screen?
Yes, sir.
Okay, right. So tree, I mean, so far you have understood a linear data structure like array, linked list, or stack queue. Uh, so in general, we can say any linear data structure can be drawn like this. Several points or nodes, whatever you can, like this. Okay, but if you connect them like this, so it is looking like this. So suppose this is the first element of the element, and this is the last element of the element. So I can draw, okay, this kind of a curve, or it may be a straight line, it may be a curvilinear the function, right? But this kind of structure is actually linear, representing a linear data structure. What if we can have some kind of this? Okay, now now let's remove, right, right, okay. So this is the linear data structure, right? Now if I change something in the structure of the arrangement of the data of the elements, something like this. So this is 1, this is 2, this is 2, this is 3, and this is 4. So I'm bringing the point labeled as 2 here, and it is connected to 1, and it is connected to 3, and then 3 is connected to 4. Okay, so this is 4. So this is now looking like this, but still we can say that it may be a linear data structure, it may not be a linear data structure. Yes, pictorially it represents a linear thing, but it may not be linear if we understand tree. Okay, okay. So what if we change something? We bring this portion here, and then okay. So if we change the structure, internal structure, something like this. So I cannot draw a curve where both the ends are open. Ignore circular linked list. So though circular linked list is a linear data structure, it actually does not exist in terms of in a circular manner, right? Actually, it has been implemented on a linear using a linear data structure. It's not like that. ঠিক আছে? So what we mean that, so can we actually draw some kind of a curve? Suppose this is your one point, so there are 4 points. Another point is over here. So one point is there. This is point node 1. Node 2 is here. node 4 is here, and node 3 is here. So if you join them, some kind of this kind of thing you are having. Okay, and it's not possible to draw such a curve from this structure. So this is this kind of linear, this kind of data structure. Pictorially, if you can see, it will be termed as a tree data structure. Yes. So this is called a tree. Okay, and also the name is very familiar to all of you. You have seen or you have heard of family tree, right? So suppose uh, this node, let's say, represents father of a family, parent, father, and then it may have the father. This family may have uh, two children like this. So let's say one male child. Okay, we can call LC and here RC. Let's say the children are labeled as LC and RC. So what we can see, we can construct here key these two are the children of F. So we connect them like this. Okay, you can say that a family or a father may have more than two children, right? Like this, three children, four children, like that, and so on, right? But we want to start with the simplest scenario of a tree, where we start with this case. A father can have maximum two children. So let's say a father is having maximum two children, LC and RC. They are named as LC and RC. Then this LC may have maximum two children, right? Like this. So we can construct the picture like this. Okay, right? This is the LC child of this LC. This is the RC child of this LC. Similarly, this RC may have at most two children, right? And so on. So this data structure is known as a tree. Okay. Fine. So what we start with, I mean, this is to start. Okay, so let's, because the tree is a very wide topic, and we want to start with few assumptions. Later on, this one of these assumption will be revised. So please keep in mind. Okay, because in some books there are a few difference between the terminologies. That's why I do not want to make any confusion. So assumptions like, okay, so before that, in this tree data structure, this kind of small circles which I have drawn, those are actually called nodes. Okay, so please be comfortable with the terminologies. These are called nodes. Okay, so this node which is placed at the top of a tree, from where other nodes are acting like children. Okay? So this node here specifically is actually called root node, or simply root. Here F is root. Okay, fine. So any node in a tree may have at most 2 children. Okay, 2 children, or in better word, 2 child nodes. Yes. Means we can have a picture like this. This node does have only a single child. This is also a possible case. Also, this is possible. This node may not have any child at all. Okay, but maximum 2 children can be is affordable by a single node in a tree. So we want to start with this concept. Okay, fine. Now, considering this root node, this node, okay, this portion, so what happens here? 1, 2, 3, 4, 5. How many nodes are there? 5 nodes, right? Among the 5 nodes, 3 nodes are here in this part of the overall picture, and 1 node is placed over here, and the one and only left, this node is placed at the top of the entire data structure. Okay? So if I don't consider this node, root node, okay, beside the root node there are many nodes, and all those nodes, you can see from the picture that some of the nodes, a set of some nodes are lying in this part, okay, one part, and the rest amount of nodes are placed in the other part. So this part is actually called left subtree. Okay, and this part is actually called right subtree. Right subtree. Okay, left subtree, right subtree with respect to f, with respect to the root f. You can see we have isolated f, and then we have visualized that one set of nodes are placed in one half, and another set of nodes are placed in another half. So this entire half is called left subtree of f. So here we can more specifically call that it's a left subtree of f, and this is the right subtree of f more specifically. Okay. Similarly, in this manner, we can say that if I consider this node, okay, let's give them unique name. If you have any confusion at any moment, so please tell me. Okay. Be clear about every important terms and concepts. Otherwise, you may have very difficulty. Anyway, so if I consider A as a node, and with respect to A, I want to find its left and right subtree. So you know, this part will be called as the left subtree of A, and this part will be called as right subtree of A. Right. So these left and right subtrees are defined on the basis of with respect to a particular node. Okay. And corresponding to B node, there are left and right subtrees, but those are empty left subtree, empty right subtree. No, a single node is present over there. Okay. So this is the meaning of left subtree, right subtree. So that means entire 5 nodes are being grouped into 2 subsets. One of the subset is containing left subtree nodes, and the other subset contains the right subtree nodes, and one node is behaving like a root node. Okay, fine. So it's kind of a partition. Okay, it's kind of a partition like this. Okay, fine. Now, okay. Next term. So you got the meaning of right subtree, left subtree, right? Okay. Now, this node, particular node, this one B. Here B is called a leaf. LEAF, গাছের পাতা. Okay. Because why? Because this kind of a special node does not have a single child. So that's why this node B is called a leaf node or simply leaf. Similarly, you can say D is a leaf node and C is a leaf node. So there are three leaves, C, D, and B. Okay, fine. Next is ascendant, descendant. Anyway, okay, fine. Now another very, very important term. So please clearly, understand that. Try to understand. One is ancestor, and and successor. So try to understand ancestor, and descendant. I will just explain this later. Yeah. Ancestor, descendant. This is the spelling. We can say here that the node F is an ancestor of node D. Node F is an ancestor of node D. Or we can say that a node F is also an ancestor of node C. Okay. So we can call that here, I'm writing this. So F is an ancestor of node C, D. Why? Because F may be a father of C and D, or F may be a father of ancestor of C and D. Let me write this, then you can say. Why? Because F is an ancestor of C and D, or F is an ancestor of C and D. Okay, simply, in other words, we can say F is a father or root. So here we don't we call a father word, we call root. So F may be root of direct root. Okay, okay, let not be mention here root, because root is unique. Okay, so for a particular tree, so which one is the root node? That is the F. So we want to fix that part. So I want to mean that F is a father of C and D, or F is a father of, okay, one node which is the father of C and D. Here, F is not a father of D or F is not a father of C. A is the father of C and D. So we call that A is the ancestor of C and D. Right? We can call it. We can call that A is an ancestor of C and D. And with respect to C and D, A is behaving like a root. If we consider this node, this portion, this subtree, only this subtree if we consider, then A is behaving like a root, and C and D are its two children. Right? So in this manner, A is a root of C and D, and F is the root of that root, A. That's why we can call that F is an ancestor of C and D.
Sir,
Okay.
one doubt.
Huh?
Sir, one doubt, sir. With respect to node C and D, sir, we can call A as the ancestor or F as the ancestor or both.
With respect to,
C and D node, sir,
huh,
A is the ancestor or F is the ancestor or
both
both.
of them are ancestors, A and F.
Okay, sir. Yes,
A
sir.
is
Yes.
the direct ancestor, means its root, and F is the ancestor. Okay. Right.
Okay, sir.
And the opposite word is descendant. So C and D are descendants of F. Okay. So if we consider A, then C is the left child or left descendant of A, and D is the right child or right descendant of A. Okay. Okay. And another thing here, এটা একটুখানি বলে রাখছি, বাট এখন যদি যেহেতু এটা এখন ইউজ হবে না, আমরা এখন এই মুহূর্তে অ্যানসেস্টর ডিসেন্ডেন্ট নিয়ে সেরকম কিছু লজিক্যালি উই উইল নট অ্যাকচুয়ালি study. So you may forget, that's not a problem. But later on, uh, while we will discuss about some other topics like rotation or something like that, then this term will be very much come into the picture, ancestor descendant. Anyway, so there is another term, left descendant or right descendant. Okay, so just explaining left descendant. So here C is a left descendant of F. Why? C is a left descendant of F, because left descendant means C is either, okay, let me write here more generally, any node, let's say n n1, okay, any node n1, okay, n, let's say nl, okay, so any node nl is left descendant of a node n a. So n a is a ascendant, right, ancestor. So any node nl is left descendant of node na if nl is either a left descendant of na or left descendant of a left descendant means left child of a left descendant descendant of NA, left child of NA. So এখানে একটু left child হয়েছে, তাহলে সুবিধা হবে, right? Okay, so this is the case. So in this case, C is a left descendant of A. How can we justify this? See, so I told you that NL is a left descendant of node NA if NL is a left child of NA. So is C a left child of F? No. What is the other possibility? Is C a left child of a left descendant of F? So what is a left descendant of F here? So to become a left descendant of F, a node has to be a left child. One of the possibilities, there are two possibilities in which a node can become a left descendant of a root, right? So one of the possibilities that node is a left child of the root node. So here A is the left child of F. ঠিক আছে? So we can call that if NL is either a left child of node A. So here node A is a left child of node F. That means we can call node A as left descendant of F. So this node A is left descendant of F. Now is C a left child of F? No. So is C a left child of this phrase, concentrate, is C left child of a left descendant of F? Yes. That's why C is a left descendant of F. পরিষ্কার ভাষায় যেন F থেকে লেফট, A থেকে লেফট 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 করে যদি যাও সবাই হচ্ছে লেফট ডিসেন্ডেন্ট হয়ে যাচ্ছে। বুঝে গেল পরিষ্কার ভাষায়? মানে সোজাভাবে যদি আমি বলতে চাই, ঠিক আছে, যে একটা নোড থেকে তুমি ট্রাভার্সাল করো, লেফটে গেলে লেফট সাব ট্রি, রাইটে যেও না, দেন মুভ ফার্দার অ্যালং লেফট সাব ট্রি, ফার্দার মুভ অ্যালং left subtree, whatever nodes you will see, all of them are left descendants of the root. And to describe this is the phrase. Anyway, now in this manner, though D is a child, D is a node present in the left subtree of F, but D is not a left descendant of F. So that is very, very important in this case. So D is not a left descendant of F, because there are two possibilities in which a node can be a left descendant of F. Either that node has to be a left child of F, or that node has to be a left child of left descendant of F. So here D is a right child of left descendant of F. So this phrase which is underlined is false. That's why D is not a left descendant of it. I hope now it is clear. Is it clear now?
Yes, sir.
Right.
Yes, sir.
Good. So in a similar fashion, we can actually define the right descendant of a particular node F. For example, here B is a right descendant of F. So if I complete this tree to become a complete tree, binary tree, then it will look like this. So let's say this is E and F. So similar conclusion we can draw here. That is, G. So here G is a right descendant of F, but not E. right? So is it clear now? So in a similar manner, any right descendant of a node is defined as, I mean, any node, sorry, any node in R is right descendant of a node any if, you know, if NR is either right child of a node A or right child of a right descendant of NA, right? So now try to understand. We can call G as a right descendant of F, but not E. So is it fine? Convinced, all of you?
Yes, sir.
Yeah. Okay. So it's clear now. Now, next term we can have here, that is one thing. Okay. One thing I have not mentioned here, though I have introduced you a tree more in terms of a pictorial manner, pictorial way, এইভাবে ঠিক আছে, একটু অ্যানালিটিক্যাল ভাবে কিছু করাইনি। তো একটা একটা জাস্ট ফ্রেজ আমি বলে দিই এখানটায়। If a node, okay, any node okay, n, if it belongs to left subtree, implies that n does not belongs to right subtree. So this is absolutely satisfiable in case a data structure is a tree. So this is one thing which is very important. Any data structure, nonlinear data structure, it's a tree if this condition is satisfied. Any node, if it is belonging to a left subtree, it should not belong to right subtree.
Sir, one doubt.
Right.
Sir, যদি এই ট্রিটাতে if we consider depicting node E, so we can say that node E is the left child of right descendant of F. Can we
Yes.
say that?
Yes, left child of right descendant of F, but it's not a left descendant of F.
Okay. That doubt.
Okay, where provided n is not a root node. Yes, so this condition has to be satisfied. And why it is important? Because suppose we have a picture like this. This is a node. This is a node. This is a node. Okay. So it's a possible tree. ঠিক আছে? right? Okay. So this is not a tree, absolutely. If I draw like this, okay. So this is not a tree, right? We have defined that a node can have at most two children. So it is having a three children. So it's not allowed. So this is not possible. But to maintain this, if I connect like this, so this node is having two children. This right, right. But this is not a tree because this node is belonging to the left subtree. Also, if you go around this, so it's a right subtree, right subtree. That right subtree contains this node. So this node belongs to both left subtree and right subtree, violating the principal condition, okay, of a tree. That's why this is not a tree. Okay, that's why. Anyway, so next we move on to a very important thing, which is uh, strictly binary tree. Okay, strictly binary. So, okay, now okay, fine. So this is a root, and it should be, you know, fully saturated. Means this node root node does have the maximum number of children, that is two, right? So let's give some name. It's of F, and this is A, and this is B. Okay. Okay. Now this node, I'm making it as a saturated node. Means it is having the maximum number of children, that is, let's say D, C, and D. Okay. So this is a root node which is having maximum number of children. This is another node which is having maximum number of children. If I proceed like this, E, and let's say this is G. Okay, this is also having maximum number of children. But this B, D, G are leaf nodes. These are leaves. Okay, like this. So this is an example of a strictly binary tree. Means, what is the definition? It is any, so I mean to say, the okay, any non-leaf nodes have exactly two children, two child nodes. Okay, so the non-leaf nodes means contain including the root node. So it is having two children. This is another non-leaf node having two children. Non-leaf node having two children, and this is another, and this is a leaf. So this is an example of a strictly binary tree. Okay, you can also have here okay, that means H and I. So this is the non-leaf node and having two children, exactly two children, two child nodes, and these two are leaves. Okay. So which one is not a strictly binary tree? But this is not a strictly binary tree. Why? Because identify the non-leaf nodes. Leaves are, these are leaves. This one, and this one. So others are non-leaf nodes, out of which these have two children, this also have two children, but this is the non-leaf node which only has a single child node. So it must have another child node to make it a strictly binary tree. That's why this kind of binary tree is not a strictly binary tree. Now is the time ki what is a strictly binary tree? Hey, what is a binary tree? So binary tree means this case. So where any node can have at most two child nodes. That kind of tree is called a binary tree. Okay. Binary tree, that means any node can have at most two child nodes. That is the binary tree. Binary means two. That's why. Okay. So another important term is there, complete binary tree. Complete binary tree means all the nodes have to be satisfied, saturated, except all the non-leaf nodes have to be saturated. So complete binary tree means okay. So this is how a complete binary tree looks like. So this is a special type of strictly binary tree. We can say that one thing we can notice here, that is, except the leaf nodes, all the non-leaf nodes. Which one are the non-leaf nodes? This one. These are the non-leaf nodes, and all the non-leaf nodes have exactly two children. So it's a strictly binary tree. But in this special type of strictly binary tree, all the leaf nodes have same depth. Now what is the depth? So in many book, depth is defined or level is defined in different manner. Okay. So we want to define level of this root node. Level is equal to 0. Okay. We want to define the root level of root node as 0. Level equal to 0. Okay. Then we want to define levels of these nodes, left child or right child of the root. Their levels are equal to 1. Similarly, all the nodes in this horizontal line, they have level equal to 2. And all these nodes in this horizontal line, they have level equal to 3. So this is the meaning of level. Okay. And what is the depth? Depth is actually the maximum level of a tree. Okay. Maximum level of level is not a term of a tree, it's level of a node. So every node does have a particular level. So these nodes have level 1, 0. These nodes have level 2. So maximum level of a leaf node in a binary tree. Okay. So here, now if it is not a complete binary tree, for example, if we consider some cases like this. So consider this strictly binary tree. So now tell me, what are the different levels of the leaf nodes, one by one. So level of E, what is level of E?
So 3.
Right. So level of F is 0, level of A is 1, this is also 1. I'm mentioning the levels over here. So this is 2, this is 2, very easy. Okay, 200. This is 3, and this is 3 here. Okay, so you can see that the levels of the leaf nodes are 3, 3, 2, 2, 2, and out of which the maximum is 3. So we can define, we can say that depth of this strictly binary tree is 3. That is the meaning of a depth. Okay, I hope you understood. And in complete binary tree, all the leaf nodes will have same levels, equal levels. Okay, and then it should be a picture like this. Okay, and complete binary tree is very important. You can find a very important and very good application, which you can see in the next semester subject in design and analysis of algorithm. Okay. Okay. Now, okay. Now, Trevor. Okay, fine. Now into okay, it's already 11:30. Whose class is this now? Mustafa sir, no?
Yes.
Yes, sir.
Traversal in binary tree. So let's, and the traversal mechanism in a binary tree are of three types. Pre-ordered traversal. Next is post-ordered traversal, and the third one is in-order traversal. And this traversal mechanism does have very important relation, very good relation with, you know, expression evaluation, which we have done using stack, infix, postfix, prefix, right? So this traversal mechanism does finds a very important relation and application in evaluating an expression using stack. Anyway, so let's take an example. Okay, right. So left, I mean, pre-order traversal means, let's we discuss one, and in the next class we will start with the other. So pre-order traversal technique. What do you mean by that? Pictorially, it means we have to initiate, we have to start from this node, which is the root. Showing some color here, right? So I'm here. Next, I will select the left subtree, but not the right subtree. So I will move around the left subtree. So I'm reaching this node here. Then I will again select left subtree, but not the right subtree. So I'm moving further and reaching here. So if there is any child, left child over there, I will move further. Otherwise, I will stop here. ঠিক আছে? So ultimately, I have come here, reached here, and stop here. And let's say I want to mention some level to these nodes. Let's say A1 A traversal mechanism you understand, other you can understand on your own. This is E and this is F. Okay, so I have reached at node C. Okay, and then I can't move further because my logic is to move further. If I leave, I can find a left child. So there is no left child. So at this moment, I am stopping over there and let's say displaying the node that is C. Okay. Next, I want to go back to its root parent node. So this is the parent node of C and D. So from here, I want to move back to B. Okay. And then I will display B. Then I want to move on to right child, right subtree corresponding to B. That means I am moving here, coming here. Is there any child? No. To stop here and display the content, that is D. Is there any child? No. So go back to the parent node, that is B. Okay. And then you go back to its parent node A. So this left subtree is finished. All the nodes have been visited, right? So this left subtree is finished. Next, I am going to A. As it is finished and A, I have reached A, so I will display A. Right? Next, I will move on to the right subtree to reach the next child node. That is the right child node, E. But I will not display it. Now, my intention is to go as left as possible. So is there any left child available over here? Okay, so let's assume there is a left child, G, for your understanding. Yes, there is a left child. So I will move along that left side, left direction, left subtree direction to reach G. Okay, and then any other child left? No. So I will stop here. So I will display G. Right? Then as there is no left, so I will go back to its parent. So I am reaching E. So all the nodes in the left subtree with respect to E are visited. So I will display E. Next, I will now move on to the right subtree because entire left subtree is done. Now I will move on to right subtree to reach toward the next child. Ultimately, I am coming over at coming at F. Is there any child left to move further from F? No. So I have to stop over here. And now I am displaying F. So if this is called a pre-order traversal in a binary tree. And while traversing, okay, this is the sequence of nodes being visited and displayed. This is the sequence of nodes being displayed. C, B, D, then A, then G, E. Okay, so pictorially it means the pre-order traversal. So, but what are the rules? Rules means, okay, first you visit the root node. Okay, that means here A. Next you move further along left subtree. In pre-order manner. So what is a pre-order manner? Pre-order manner starts over here. Visit the root node. So move further along the left subtree. Next, you go to move further along right subtree once the left subtree is done, is completed. Okay, so that's the meaning. So first you visit the root node A, then you go to the left subtree with respect to A. Now, what is the pre-order traversal? That means you have to go to the next root of the left subtree. So this is the root of the next the remaining left subtree, right? So you're visiting over here. And from B, you are now finding the root of the left subtree. With respect to B, what is the left subtree? This portion. And what is the root? C. That means move further along left subtree in P order means you are going as left as possible, not going towards any right branch. Always you are trying to follow a left branch of a left subtree, and you will reach ultimately at the dead end of the left subtree, which is the leftmost element, leftmost leaf. So once you visit the leftmost leaf, then you go back to its parent node, then visit and then move along the right subtree. So what is the pre-order means in other color, green color. So with respect to BCD, I can define the pre-order traversal means somewhere from B I have moved to C, then I go back to B and then D. So this is the meaning of pre-order traversal, CBD. See, from B I have moved to C, displaying C, then B, then D. So always this kind of manner. So if a tree is like this, here is a node, here is a node, here is a node. So pre-order traversal means this kind of thing. Okay. Okay. So you need to actually practice with several examples and try to find out the pre-order traversal, and then it will be more clear. So with this, I want to stop here. If you have any doubt, you can ask.